Is it visible?
Yes, ma'am.
Okay. So we have started with this problem, and we actually completed the load calculation part, and we also calculated the bending moment and shear force acting on the beam. Okay. So for this plan, we started design of beam B2, and we also recalled how the load is transferred from the slab. In this example, all these slabs, or rather we are designing B2, so we have to consider these two adjacent slabs, S1 and S2. Both these slabs are one-way slabs, so the load transferred from these slabs is calculated. Then the load coming from wall was also calculated, self weight was also calculated, and then further we calculated the bending moment and shear force. So this was the calculation part. I will quickly go through the calculation part. We decided first the size of the beam, then depth of the beam, in which width and depth of the beam we decided. We calculated effective depth of the beam. Then we also discussed about how to consider depth of the flange, because in case of T-beam, some of the portion from the slab will behave as a part of, or will work as a part of the beam. So that total flange width is considered by using this formula. This formula is given in IS 456. Then further we calculated the effective span, then the load calculation. So load coming from slab we have to we calculated first. So first we have calculated the load, total load acting on the slab, and then the load shared by the slab S1 and S2 separately, total load from slab, both the slabs, then load coming from wall, self weight of beam, and finally we calculated the total load. We applied the factor of safety and we calculated the design load or ultimate load, and then we calculated the ultimate bending moment and shear force. Okay, so today now we will continue the same problem for next step. So the next step, we have to calculate the moment capacity of the beam. So let us calculate the moment capacity of the beam. So just write down point number 5, or next step, as moment capacity. Okay, so I will go to the next page directly. So here, so the next point is finding or calculation of moment capacity. Now, if you remember, we have already discussed during the analysis of flange beam that in case of flange beam, we have to consider 3 different cases depending upon the depth of the neutral axis. So I will go back to your presentation here, slides here, and I have included this particular slide to recall the concept again. So the first case, we consider it as a neutral axis inside the flange, that is the XU is less than the depth of the flange. In this case, all the formulas which we have used for the rectangular beam, they are applicable as it is. Only the difference is that instead of B, we have to consider BF, that is width of the flange, for all calculation. Second case is that when the neutral axis is not in the flange, when it shifts below the flange, that is when it lies in the web. Now in the web, again, this case is subdivided into 2 parts, whether the rectangular part of the stress block is less than DF or greater than DF. So accordingly, there are 2 cases. Case number 2A, in which it is assumed that XU is less than 7/3 DF, and case number 2B, in which XU is greater than 7/3 DF. In both these cases, the formula for calculation of XU, the formula for calculation of MUR and AST goes on changing. Because when the XU is lesser than 7/3 DF, the depth of the stress block is considered as YF. Okay, and accordingly, the YF formula is used and the further calculations are done. Second case, that is case 2B, in which when XU is greater than 7/3 DF, the total depth of the flange is considered, instead of small d, we consider capital DF, and we do all the calculation, in which the rectangular part of the stress block is more than depth of the flange. Okay, so now when we design the T-beam, we have to decide which case we have to consider. Actually, when we design the beam, we don't know initially where is the depth of the neutral axis, where the XU lies, what is the value of XU, where the neutral axis lies in the beam, whether it is inside the flange or whether it is within the web. Okay, so to avoid the complications in the calculation, only two cases are assumed in practice. The first case is that we consider initially that the neutral axis lies inside the flange and we calculate the MUR, that is the moment of resistance shown by the beam when the assumption is that the neutral axis lies inside the flange. Accordingly, we calculate the moment of resistance. That moment of resistance, we call it as mu1 because that value is for our first assumption that neutral axis lies in the flange. And we compare that mu with the bending moment acting on a beam. Now, if this mu1 is greater than the bending moment acting on a beam, then our assumption is correct. And we proceed further by considering xu less than df. But if your mu is coming less than mu1 is coming less than mu, it indicates that our neutral axis will lie in the web. See, as the neutral axis go on changing, that is, as the depth of neutral axis goes on increasing, obviously the MUR value will go on increasing or decreasing. Just tell me. Everybody are there in the class, right?
Yes, ma'am.
Huh. So if
Yes.
X2 goes on increasing, what will happen with MU? Whether it will increase or decrease?
Directly proportional.
It is directly proportional to XU. Correct. So if XU goes on increasing, our MU value, MUR value will also go on increasing. Okay. So to increase further the MUR, we have to increase the depth of neutral axis. This is the indication when our MU1 comes less than MU. That is the bending moment acting on the flange. Okay, and based on this concept, we consider that we have to consider the second case in that in this problem, that our XU is greater than DF. Now, when we consider second case, again there are two cases. If you consider case 1, that is this case 2a, that is your XU is less than 7 by 3 DF, we need to consider YF also, and YF formula consists of XU. So we have to assume some XU value initially, calculate the YF, then calculate MU, check it MUR, then check it with the bending moment. All these lengthy process go on increasing. So instead of considering the case 2a first, we go to directly case 2b and verify whether it is whether XU is greater than 7 by 3 DF or not. And then we further proceed. Okay, so in short, the design of T-beam is little bit complicated as compared to singly reinforced or doubly reinforced section. Okay, practically how we design? Practically, we always consider that the neutral axis lies inside the flange, and we always do the calculation by based on this assumption because our all further calculation reduces, all further calculation part reduces, and to achieve the easiness in the calculation, we always consider case 1. Now, how to consider case 1? Always how to keep the XU within the flange, that we will see now when we solve the problem further. Is it clear to everybody the concept of flanged beam? So how the calculation part becomes complicated? Is it clear to everybody?
Yes, ma'am.
Yes, ma'am.
Okay. So let us assume first here for calculation of moment capacity that the neutral axis is in the flange. Okay. So just write down assuming neutral axis lies in flange. Now, when the neutral axis lies within the flange, I will go back to the diagram, whatever we have drawn last lecture. This is the flange, this portion is flange, and my neutral axis lies within the flange. Now, at what depth? That we don't know. So instead of assuming the XU value, we consider directly the depth of the flange. XU equal to 120. Because instead of assuming XU less than DF, we consider XU equal to DF. That also indicates that our neutral axis lies within the flange. Okay. So for the further calculation here, when we assume that the neutral axis lies in the flange, take XU equal to DF, that is depth of the flange, which is equal to 120 mm here in our problem. Okay. Now, as the neutral axis in flange, our MUR formula is the same one which is for rectangular singly reinforced beam. Okay. So here I will write down MU1 instead of writing MUR, because this value of MU we are calculating for this assumption. Okay, this is our assumption. So my formula is 0.36 FCK BF into XU into bracket D minus 0.42 XU. Okay, so put all the values in this equation and tell me what is MU1 value you are getting. So this is 0.36 into FCK is 20 into BF. What is BF value?
Ma'am, FCK 25.
FCK is 25. Let me check. I forgot the problem statement. Okay, all this is the load calculation. Okay, all right. If it is 25, we'll consider 25, no problem. But tell me what is BF value? 2020, right? 2020 value, BF. We have calculated last time.
3000 mm.
Yes. So this is 25. This is very boring now. On Word. Okay, this is 25. BF value is 2020 mm into XU is 120. Tell me now effective depth.
450 mm.
450 minus 0.42 into 120. So MU1, let us calculate this one. What is the value? Students?
871.76.
871.76. Okay. Kilonewton meter, right? Unit.
Yes.
Now compare this value of MU1 with the bending moment which we have calculated in the previous lecture. So the bending moment calculated was 261 kilonewton meter, right? And this value is coming as 871. So this value is greater than MU1, sorry, MU. So this indicates that the neutral axis lies in the flange only. Okay, so this value slightly indicate us or give the idea about the XU value. If MU1 is less than MU, it means XU value we need to increase, because see, whenever we complete any design for any beam, our main criteria is that the moment of resistance shown by the beam or any section should be greater than the actual moment acting on a beam. Then and then our design will be safe. Okay, so if this condition is getting satisfied here, it means whatever is our assumption is correct. The neutral axis is lying in the flange. Is it clear? Because this is very important step. if this will come less than mu1 is coming less than mu, then we have to assume the second case, that is xu is greater than less than 7 by 3 df, in which again we consider xu equal to 7 by 3 df and do the further calculation. Okay, so this is a procedure, but for sake of simplicity we always do the design in this fashion. Now what to do in the exam, that will be your next question. That suppose in the examination my mu1 value, this value is coming less than mu, should I proceed to the next step, that is consider xu equal to 7 by 3 df and do the further calculation? Those calculations will become complicated again. So to avoid that, anyways you are designing the beam, it means you are deciding its dimension. You can change the dimension, but only the thing, all the earlier steps you need to repeat again if you are changing the dimension. Now how to change the dimension? Let us have a look. See this mu1, suppose if it is coming less than mu, I want to increase this value. Now in this value, if I want to increase mu1, look at the formula of mu1. In this formula, we cannot change 0.36, it is constant. FCK we cannot change because it is defined. BF we can increase, right? Because we have decided this BF value based on the formula. So what is the formula? The formula is given in the code. The same we had already written here, BF formula. So by making use of this formula, we have calculated BF and we have adapted the same value whatever we have obtained directly from calculated. We have only cross-checked it with the limiting value 3000. But in the design, we can increase this value up to 3000. So to increase mu1, I can increase BF. See, initially, right now we have adopted this value. If I want to increase this, we can increase, but the limitation is 3000. So I will increase this value straight to say 2500, and I will check now the mu1 value. Automatically, my mu1 value will increase. Okay, why we should we do this? Because my mu1 is coming less than mu, and I want to increase that value. In that case, this is the another way. Okay, if you don't want to increase BF, you can increase depth of the beam, because width and depth, these two sides of the beam or dimensions of the beam, we have already decided earlier. But now to satisfy this condition, I can redesign all this. Okay, so my suggestion in the examination, that suppose your mu1 is coming less than mu, better you increase the mu1 value by increasing either BF or D or both. Okay, because you have to decide the size of the beam. Now suppose practically if there are restrictions for increasing these BF and D value, as we do in case of doubly reinforced section. Why we go to doubly reinforced section? Because practically many times there are the restrictions to increase the depth of the beam. Suppose that is the only case that we cannot increase the D beyond a certain limit, or cannot increase BF beyond a certain limit. In that case, then we have to consider second case and we do the calculation. Okay, but this is a practical application. I'm telling you exam point of view, that in examination, forget about the limitation of D and BF. If it is not mentioned in the problem statement that there is a restriction to depth and restriction to width of the flange, then you can simply increase these values and increase mu1 if it is not mentioned in the problem statement. If it is mentioned, in that case again you have to go as per the steps. Is it clear to everybody?
Yes, ma'am.
Okay, shall we proceed further?
Yes, ma'am.
Only one student is talking with me. Others, I hope they are paying attention.
Yes, ma'am.
Okay. So the moment capacity we have already calculated mu1, which is mur now in our case, because it is confirmed now that the neutral axis is lying in the flange. So the next step is calculation of AST. So I will simply write down the sixth step here, calculation of AST. Okay, now to calculate AST, whatever the formula we have used for rectangular beam, or singly reinforced beam, the same formula we have to use here. Because once your neutral axis is lying in the flange, the T-beam will behave like a rectangular beam for calculation. For calculation. So whatever the formula we have used for rectangular beam, same formulas we have to use here. Okay, so what is the formula for AST? 0.5 FCK upon Fy into bracket 1 minus under root 1 minus 4.6 mu divided by FCK BF D square. BF value we have to consider for flange, into BF into D. Okay, so by making use of this formula, now we have to find out the AST. So let us put all the values here in the AST formula and find out AST. So this is 0.5 into FCK is 25. What is Fy value?
415.
415 into bracket 1 minus root. Again, 1 minus 4.6 into mu. So what was the mu value? It was 200 someone.
261 kilonewton meter.
Yes, so 261, this is in kilonewton meter, and all other values we have written here in Newton mm. So let us multiply this by 10 raised to 6 to convert the value into Newton per mm square. FCK is again 25 into BF is 2020 into D is 450, right? 450 square. Okay. Multiplied by again, I will write down now. So this is multiplied by 2020 into 450. Okay, BF into D. So tell me AST value now.
Ma'am, and we have considered here it as if a rectangular beam, no? Ma'am, but in this case, the XU is equal to the depth of the flange part. But if in case XU will be less than the depth of flange section, then we can consider it as rectangular only.
Yes, rectangular only. If your XU is lying within the flange, whether the value is equal to DF or less than DF, the XU is lying in the flange. In that case, we treat it as a rectangular beam with width of the beam equal to BF.
But the portion which is below, which is the part of the beam,
That is there. So it is still T-beam but for calculation purpose, we are using these formulas. We already discussed when we studied about the analysis of flange beam, right? So you just open that recorded video. I think it was lecture number 9 or 10. I don't remember now. I think it is 9, lecture number 9. So just check the video of lecture number 9. You will get the concept clear. Okay. So I have explained everything along with the diagrams.
Okay, ma'am.
Okay. Tell me the value of AST now.
1657.39 mm square.
Again.
1657.39.
1657.39
mm square.
Okay, mm square. Again, we have to compare these values with minimum and maximum AST. Okay. So this value should be greater than AST minimum. What is the formula of AST minimum?
0.85 BD upon Fy.
Okay. Now here B is to be considered as BW, huh? BW into D upon Fy. Okay. So tell me the value. 0.85 BWD upon Fy. BW means width of the web. Huh? What was the value for width of the web we have assumed?
300.
Okay, so use that value in the calculation and tell me the value now.
276.51.
Okay. And AST should sorry should be less than the maximum value AST max. So let us calculate the maximum value. The formula is again 0.04 BD, right? So BW into D here. So what is the value you're getting here?
$5,400.
5,400 mm square. Okay. So our AST value is within the range of minimum and maximum value. Let us find out now the number of bars. So we will assume here. Now, if you consider the AST value is
Ma'am,
much higher. Yes.
in the AST max, instead of small d, it should be capital D, right?
Right. Correct. It should be capital D.
Ma'am, then it's 6,000.
Okay, the value is also changing. All right. This value is 6,000 then. Okay. Okay. All right. Now, if you observe the value of AST, it is 1,657. And the entire AST, when we provide the steel, we provide in case of T-beam. I will go back to the diagram of the T-beam here. We have to accommodate all the steel here within this width. Okay. So if you assume 16 mm diameter, obviously the number of bars will be more because the area required is around 1000 or more than 1000. So obviously, if we consider 16 mm diameter of the bar, the number of bars required will be more, and then it is not possible to provide all the reinforcing bar within the width of 300 mm. Either we have to provide it in 2 or 3 layers here. Okay, so instead of that, if the area of the steel coming is higher, not say 500, 600, instead of that, if it is coming 1000, go increase the diameter of the bar. Okay, so that our problem of providing the steel reinforcing bar in 2 layers or 3 layers will be eliminated, and we will be able to provide the number of bars in one layer only, in one row only, which will get which will satisfy the check for width also. Okay, so now as the area of the steel is higher, it is more than 1000. I'm assuming here the bar diameter as 25 mm, not even 20 mm, or I will show the calculation by both. I will consider initially as 20 mm. Let us assume bar diameter of 20 mm. Okay, so I will calculate now the number of bars is equal to, the area is 1657.39 divided by area of the single bar, pi d square by 4. Tell me number of bars.
5.27.
5.27. It means I have to provide 6 bars. Okay, 6 bars. Now just imagine there are 6 bars of 20 mm diameter, plus I have to provide certain spacing between the 2 bars, which normally comes out to be 25, right? So 25 multiplied by 5 spacings, okay, plus there are 6 bars, so it will be 6 into 20. This spacing itself, this total width itself is coming as 245, plus I have to provide the side cover also on both the sides, so the total width is exceeding beyond 300. Okay, so in this case I have to increase the bar diameter. Is it clear? Are you getting this point? There are 6 bars, so 6 multiplied by 20, what is the value you are getting? It is 120. Plus I have to maintain a spacing, minimum spacing between each bar as 25 mm. So there are 6 bars. So if I will consider 1, 2, 3, 4, 5, 6 bars over here. So there are total 5 spacings. So 1, 2, 3, 4, 5 multiplied by 25 is normally the spacing. So it is 125 plus 120, it is coming 245. And normally I provide the side cover of 30 mm on either side. So 30, 30 both sides 60. So 245 plus 60, my value is coming as 305, which is exceeding 300. Okay. So when the area of the steel coming is higher, more than 1000, better to assume the larger bar diameter. Okay. So now I will erase this. And we will do the calculation for 25 mm bar diameter, so that our check for width will be satisfied. Okay, so I will immediately write down here. Let us assume bar diameter of 25 mm. So number of bars, tell me the number of bars again here. 1657.39 divided by area of the single bar.
3.37.
Yes, 3.37. It means it will be 4 number of bars. So let us now check again the width. So I will write down here check for width. What happened? Okay. Check for width. So what is our formula? The required width is calculated as 2c1 plus c2 into bracket n minus 1 into bracket n into 5. Is it correct? Formula?
Yes, ma'am.
What is C1? What is C1?
30.
Sorry. What is C1?
30.
30, huh? 30 mean, but what? Is
Side
it a
cover.
side? Huh, it is a side cover which we normally assume as 30. So 2 into 30 plus C2 is the spacing between the bars. So it has a criteria greater of the 3 criteria, the larger bar diameter. Second is the larger of the variation in the bar diameter. We have provided all the bars having the same diameter. So First will be 25, second will be 25, and third. What is the third criteria?
Maximum size of aggregate.
Aggregates plus 5 mm.
Plus 5 mm. So normally the nominal maximum size of aggregate is taken as 20 mm plus 5. So that is also coming 25. So C2 will be 25. Okay. So this is 25 into bracket n. N is number of bars, right? Which are coming 4 here minus 1 plus 4 into bar diameter is 25. So B required value. Tell me the value.
$235.
235 mm, which is less than the B value. What was the B value? BW here, because we are providing the steel in the bottom. Na? So BW is 300. So this is okay. The check is satisfied. Okay, so if we have used the 20 mm bar diameter, this will be 6. So these values, this is 30 into 2 plus 25 into 6 minus 1 plus 6 into 20. The value is coming around 305, which will exceed your BW. So the check for width will not be satisfied. In that case, either we need to, normally we reduce the bar diameter. Okay, sorry, we increase the bar diameter to get our check satisfied. Is it clear to everybody? Steps up till now. And the next step is design for shear, which you are going to do or complete as a homework. Okay. The next step is design for shear. Now, how my beam will look? I will just draw the diagram. Once you complete the design for shear, the shear reinforcement details you can show in the diagram. So I will draw a diagram over here. So this is my T-beam. Okay, and there are total 4 bars of 25 mm. So 1, 2, 3 and 4 bars are located here in the tension zone. 2 bars we have to always provide in the compression zone. So these are the 2 bars. And now I have to show the stirrups also. So the stirrups will run here like this. Please make use of scale when you draw the diagram. Okay, so these are the stirrups. So you have to give the dimensions for or details of the stirrups. I don't know whatever is the design for the shear that you have to write down here. Then other details you have to show here. BF we have adopted as 2020 mm. So that I have written. The depth of the flange is 120 mm. Then width of the beam is 300 mm. And the overall depth of the beam is, I think, 500, right? So because we have considered D as 450, this is overall depth. Okay, and the details of these 4 bars of 25 mm diameter. Okay, so these diagrams are also expected when you complete your design. In the examination also, draw the diagram when you complete your design. Okay, the other details, that is the reinforcement details, you are going to tell me. Okay. Normally in the compression zone, the minimum reinforcement is provided like this, 2 bars of 12 mm. That is sufficient. Okay, because though What is the purpose of providing this steel in the compression zone? Do you know that? Students? Are you listening to me?
Yes, ma'am.
So can you tell me why we provide the minimum reinforcement in the compression zone always?
मॅम टेन्शन झोन मध्ये जास्त एन्फोर्समेंट लागते म्हणून.
नाही, पण मग आपण कॅल्क्युलेशन तर टेन्शन झोनच केलंय ना, कॉम्प्रेशन झोनचं केलंच नाही. आपण हा डब्ल्यू म्हणून नाही डिझाईन केलेला, तरी सुद्धा 2 बार दिलेले आहेत नॉमिनल. का बरं?
शिअर
कशासाठी?
स्ट्रेंथ साठी.
शिअर स्ट्रेंथ साठी म्हणजे
मॅम कदाचित तिथे कॅन्टिलिव्हर आहे म्हणून होऊ शकते
नाही,
स्ट्रेंथ कमी.
नाही, नाही. It is not a cantilever, it is a T-beam. See, for singly reinforced beam, also we provide these 2 bars in the compression zone. Rectangular beam. Yes. So that is also homework for you. Now, this question I have asked to you, you have to find out the answer for this. Next lecture, I will definitely give the answer. But you just try out. Yes.
स्टीरअप्स एकत्र करण्यासाठी.
Correct. To provide to support the stirrups, that is the one reason. But suppose I'm not providing the stirrup, I'm not considering any shear design. In that case, I will not require to provide these stirrups, right? Still, we provide 2 bars. Why? Find out the answer. Next lecture, I will ask you this question. I will definitely give the answer in next lecture. But, yes? Yes? Find out the proper answer. असं उगीच असं टुक्के मारू नका. प्रॉपर आन्सर फाइंड आउट करा, सर्च करा.
Ma'am, to prevent from shocks and impacts.
No. That is not the correct answer.
Ma'am, to increase resisting moment.
No. Resisting moment is considered based on this AST only. We have you considered this in the any calculation further? MUR मध्ये कुठं आपण घेतलंय का हा AST, किंवा समजा तुम्ही दुसरा फॉर्म्युला वापरला 0.87 FY AST इंटू ब्रॅकेट D मायनस 0.42 XU, तिथं सुद्धा आपण हाच AST वापरतो, हे नाही वापरत. त्यामुळे MUR चा काही संबंधच नाही तिथं. ओके मॅम?
तुम्ही डब्ली रेनफोर्सच्या वेळेस सांगितलं होतं ते रिव्हर्सल वाला, तो एक रिझन असू शकते.
दॅट इज फॉर डब्ली ना. रिव्हर्सल स्ट्रेसेस हे काय प्रत्येक बीमला नसतं ना. जिथं असतं तिथं आपण डब्ली रेनफोर्स डिझाईन करतो. तिथं आपण प्रॉपर डिझाईन करून ASC काढतो. इथं एरिया ऑफ द स्टील इन कॉम्प्रेशन झोन. मग तो 2 येईल, 3 येईल, 4 बार्स येतील, जे काय येईल तर येईल डिझाईन प्रमाणे. पण जेव्हा आपण सिंगली रेनफोर्स बीम डिझाईन करतो तेव्हा सुद्धा मिनिमम 2 बार हे वरती कॉम्प्रेशन झोनला असतातच. त्याला आपण काही कॅल्क्युलेशन वेगळं करत नाही. आपण 12 mm चे 2 इथं देऊन टाकतो. Why? Find out the reason. Okay? Now, remaining 15 minutes are there. I want to start with the next point, that is design of continuous beam. Yes?
Ma'am, for the design of shear reinforcement, FYS 250 घ्यायचा आहे ना?
हा, आता ह्याच्यात परत मी एक क्लॅरिफिकेशन देते. कधी कधी माइल्ड स्टील न वापरता टॉर्च स्टील सुद्धा वापरतात बरं का शिअर एन्फोर्समेंटला. म्हणजे पूर्वी स्ट्रिक्टली आपण माइल्ड स्टीलच वापरायचो, पण आता माइल्ड स्टीलचं मॅन्युफॅक्चरिंगच कमी झाल्यामुळे टॉर्च स्टील पण वापरतात 8 mm किंवा 10 mm चं. सो मी जेव्हा तुम्हाला स्टेप्स लिहून दिले त्याच्यामध्ये यू हॅव टू ऍझ्युम द डायमीटर ऍज वेल ऍज ग्रेड ऑफ स्टील असं दोन्ही स्पेसिफाय केलेलं आहे तिथे. इफ यू रीचेक द स्टेप्स फॉर डिझाईन फॉर शिअर, पुन्हा एकदा चेक करा व्यवस्थित, तर यू हॅव टू ऍझ्युम बोथ. तुम्ही ऍझ्युम करायचं की तुम्ही माइल्ड स्टील वापरणार आहात तिथं का टॉर्च स्टील वापरणार आहात. If you are using mild steel, then Fy will be 250. If you are using Tor steel, take Fy equal to 415. So you have to specify both in the design. Okay?
Yes, ma'am. And is there any criteria to select which one we have to use?
No criteria. No criteria.
And we don't have to do the curtailment in this question, no?
For design of beam, no need. आता ह्या गणितामध्ये see when you solve the problem, specific problems based on design for shear, मग तेव्हा तुम्ही curtailmentचा विचार करा. आता नका करू.
Okay, ma'am.
All right. Shall I proceed further? हे आता वर्ड फाईल मी तुम्हाला VLP वरती आज परत अपलोड करते so that all the steps you can see there also. Okay, so I will close this now and we will go back to the next slides, that is continuous beams. Okay, I'm considering now the next type of a beam, that is designed for continuous beam. So just note down this problem statement. We will at least share or you can note down the problem statement and diagram. We will complete this part today at least. Are you writing?
Yes, ma'am.
I will simply read the question. For the central line plant shown in figure, design beam ABCD for the following data. First, thickness of the slabs or thickness of all slabs equal to 120 mm, floor to floor height 3 meter, width of brick masonry 150 mm, floor finish on slabs 1 kilonewton per meter square, live load on slab 3 kilonewton per meter square, width of supporting column 300 mm. M25 concrete and Fe 415 grade steel are used. So once you finish writing this problem statement, let me know. I will show the diagram. Have you completed problem writing? Students?
Yes, ma'am.
Okay. Take down this diagram now. So you can see here there are 3 slabs, S1, S2, S3, and there are total 8 columns located at A, B, C, D, E, F, G, H, and these are the beams. A, B, C, D is one continuous beam. E, F, G, H is the another continuous beam. A, E, B, F, C, G, D, H, all these are the flanged beams. A, E and D, H, these will be L beams, whereas B, F and C, G will be T beams. Okay, and A, B, C, D is a continuous beam which we have to design in the problem. Okay. take down the diagram. Is it over?
Yes, ma'am.
Okay. How to design this beam now, ABCD, and how the load is considered on this beam, and what happens with the moment. Everything now I'm going to explain you. Just a minute. Let me open this Word file now. Okay. Before going to the first step, let me explain all of you first what happens in case of continuous beam. So I will draw here a diagram of this continuous beam. So this is first column, say A, then B, C, and D. Okay, this is our continuous beam, and it is subjected to some loading, UDL. Currently, I don't know what is the value, but
मॅम
there.
तुमची वर्ड फाईल दिसत नाहीये.
Oh. Mm. आता दिसते?
हो मॅम.
Okay. So this is our beam ABCD with the support at A, B, C, and D. These are the location of columns as per the diagrams. And there is some load acting on this entire beam ABCD. So this is our continuous beam. Now how the moment we calculate for continuous beam, or how the moment distribution is there on the continuous beam. Can you recall? I want to draw a bending moment diagram here for this beam. How it will be. Students, how will be the bending moment diagram? सगळं विसरलं का? Mos 1? Okay, so it will be somewhat like this, if you remember. Am I right?
Yes, ma'am.
So this portion is your positive or sagging movement zone, and at the support there will be the negative movement or hogging bending moment. Okay, now if you go back to this diagram of the slab, okay, this is your actual slab. This is visible to you, na? Diagram of slab.
Yes, ma'am. Yes, ma'am.
So here, when I want to design ABCD this beam, this is actually supporting 3 slabs, and this beam behaves like a flange beam again. But now here in this case it is L beam, because there is nothing on the another side of this beam ABCD. This is a plan, huh? So there is nothing on the another side of the plan of the beam ABCD. So this beam will not behave like a T beam. Okay, it will behave like a L beam. Now I have to design this entire beam as a flange beam only, but as a L beam. But whether it will behave like a L beam for its entire span or not, that we have to understand based on now this diagram. Okay, now if you consider the midspan of AB, AB is a small span of a beam, ABCD we have considered. If you consider the midspan of beam AB, it is subjected to sagging bending moment. Now what happened in case of sagging bending moment? Your beam, suppose this is a part of a beam, because of the loading, it will bend like this, right? So if this is a cross section, the portion below the neutral axis is in tension and portion above neutral axis is in compression, right? So here in the mid-span zone of beam AB, here there is a slab. Okay, so how my beam will look? It will look like this. This is a cross section. L beam. It will look like this. Okay. Now, as the midspan of the beam is or has to resist the sagging moment, there will be tension in the bottom and compression in the top portion, right? That is, the portion of the slab in the midspan zone is in compression and the portion of the beam, L beam or the web of the beam is in the tension. Okay, or in short, for the sagging bending moment, compression is at the top, whereas for hogging bending moment, the compression is at the bottom. The same thing if I want to discuss about this hogging bending moment, this portion, how the beam will bend. In that case, it will bend like this. So there will be compression in the sorry, there will be tension in the top portion and compression in the bottom portion, right? So in case of hogging bending moment, what will happen? The compression is at the bottom of the beam, that is in this region. In the bottom of the beam, there will be the compression. Okay, now what is the assumption of the limit state? As per the assumption, the tensile strength in the concrete is completely neglected. So if the concrete is in tension zone, we have to neglect the concrete strength in the tension zone. Okay, so in case of a continuous beam where there is a sagging bending moment, the portion of the slab is in the compression side of the beam and hence it is considered as a part of the beam. Okay, the slab portion, this portion is in the compression zone of the beam and hence it is considered as a part of a beam, and hence in the middle span of the continuous beam or mid span of the continuous beam is designed like a L beam or a flange beam. What is happening in the over the support? Over the support there is a hogging bending moment. In hogging bending moment, the compression is in the bottom of the beam. Okay, how the beam is bending? It is bending like this. So if this is the beam, the compression is in the bottom of the beam. So if this is the beam, in this case, this portion is in compression. This part is in compression, whereas this portion is in tension. It is exactly opposite, right? So in this case, the slab, where it is lying now, it is in the top part. The slab is in tension. Okay, the concrete present in the slab is in tension and we have to ignore it. So the slab part is ignored above the support in case of beam, in case of continuous beam. And hence, if I want to draw the cross section for the different spans in continuous beam, for the mid span of continuous beam, I have to design the beam like a L beam, okay, in which I have to consider the resistance shown by the slab also. Whereas near the support, the beam is to be designed like a rectangular beam. Here, at both the support, continuous support, I have to design the beam like a rectangular, whereas in the mid-span zone, my beam is like a L beam. Are you getting this point or not? Students?
Yes, ma'am.
So I repeat here, in case of continuous beam, now the entire continuous beam as per the diagram, we have to design like a flange beam. It will be L beam. Now if the L beam I have to design, the mid span, for the mid span, there is a sagging moment. So there is a tension in the bottom and compression in the top. So the concrete present in the compression part is majorly because of the slab. So slab will take part in resisting the force because it is in compression. Okay, whereas over the continuous support, the slab is in tension zone because there is a hogging moment. In case of a hogging moment, there will be tension in the top region of the beam and compression in the bottom region. So there is a slab in the top portion, and hence the tension in the concrete as per the assumption is completely neglected. So we have to neglect the presence of slab over here, and we design that portion of the slab as a rectangular beam. So in the design, when we calculate the moment of resistance shown by the beam, we have to divide the entire beam into different parts, like the midspan of AB, midspan of BC, midspan of CD. For that, we have to calculate MUR by assuming it as a flanged beam. And over the support, continuous support, that is at B, at C, the same beam we have to treat like a rectangular beam, and we have to calculate moment of resistance and AST accordingly. Okay, so in short, the design for continuous beam is a very lengthy process. We have to first analyze the beam. Now you can see simply by observing the diagram itself, you can understand that we cannot easily find out the moments, because we have to find out the support moments, we have to find out the midspan moment. So we have to make use of moment of distribution method to calculate the moments, total moment acting on each span and at the support also. And based on that, we have to further find out the moment resisting capacity of the continuous beam. Okay, so this is a lengthy process, and I think we will require at least 3 lectures to complete a single problem of continuous beam. So shall we proceed today further, and can I extend the lecture by half an hour? I'm asking you because I have not discussed this yesterday or in the last week, that I'm going to extend the lecture. So if you say yes, I will extend the lecture and we will finish at least the load calculation part. Otherwise, I need to arrange the extra lecture then. Tell me quickly, all of you. What should I do? Guys? Huh? Your voice is breaking.
Ma'am, we are having ma'am, can you take extra lecture after some time?
You don't want to extend today?
No, ma'am.
No, ma'am.
Okay, so Wednesday I will not be able to conduct your regular lecture because I have to visit our college campus for some other work. So online lecture conduction on Wednesday is not possible. So tomorrow I will try whether I will get the extra lecture at 11:15 timing only, because that is easy way for me to extend the lecture. Okay, so I will. Whose lecture is there tomorrow at 11:15? Can you tell me? Just check your timetable and tell me.
Ma'am, it's
Ma'am, elective
elective.
subject. Elective subject.
Oh, elective, I can't manage it because 2 teachers I have to make a request. Not possible Tuesday then. And you have practical also, na? Afterwards, 3:30.
Yes, ma'am.
Difficult tomorrow to arrange the extra lecture then. I will
Ma'am,
check
Friday?
on Thursday.
Friday exam. Ma'am.
काय
Friday exam.
मला काहीच ऐकू येत नाही, खूप
मॅम,
डिस्टर्बन्स आहे.
फ्रायडेला फाउंडेशन इंजिनिअरिंग आहे, तवा करा.
नाही, मी थर्सडेला घेते ना. थर्सडेला माझं 2:15 ला ते मी 11:15 ला घेते. शिफ्ट करून, म्हणजे मग आपल्याला 1-1:30 पर्यंत एक्सटेंड करता येईल लेक्चर. चालेल ना?
Yes, ma'am.
Okay. I will try to adjust Thursday's lecture itself. Instead of 2:15, we will consider at 11:15. तुमचे काय ओरल बिरल नाहीये ना? HWRE चं लेक्चर आहे ते.
मॅम प्रॅक्टिकल मध्ये असतात ओरल्स.
लेक्चरच्या वेळेला म्हणजे ओरल इन द सेन्स कंटिन्युअस इव्हॅल्युएशनची टेस्ट वगैरे नाही आहे ना थर्सडेला?
नाही मॅम ती फ्रायडेला आहे.
हा HWRE ला काही नाही ना थर्सडेला? Okay, I will discuss with sir only. No problem. All right, then let us give now the attendance. And I request everybody to attend the next 2 lectures without fail, because continuous beam design, it requires minimum 2 to 3 years to complete a design of a single problem.